Swayam Prabha. Digital India. Educated India.
Welcome friends to this fourth lecture of week 8 of this NPTEL online certification course of environmental soil chemistry. We are talking about some of the important inorganic pollutants so we have covered a lot some of the important trace elements which are potential pollutant for soil. So we in the last lecture we have discussed about the molybdenum, that is MO, and we started discussing it. The sources, remember, sources of molybdenum varies from parent materials, fertilizers, sewage sludge, coal combustion, and also mining process, and it has got 5 isotopes, and common oxidation states are basically from 2, 3, 4, 5 and 6. However, the predominant forms are 4 and 6. So, if we consider the molybdenum in the soil environment, its concentration generally varies from 0.5 to 5 ppm, and but in the organic soil the concentration could be 3 times higher than this, because organic matter has more binding capacity of the trace elements due to the chelation action. And if you consider the distribution in the soil, molybdenum accumulates in the soil upper layer due to its preferences for organic matter. One important pattern you have seen that most of the trace elements like copper, lead, they have high affinity towards organic matter. So, molybdenum also has similar kind of affinity. So, basically they tend to get bound by this organic matter due to the chelation action, and leaching of molybdenum is enhanced in alkaline conditions. So, molybdenum get leached in alkaline soils. If we consider some of the different forms of molybdenum in the soil environment, first of all is fixed within the crystal lattice. Secondly, it is adsorbed on soil material as an anion, and then bound with organic matter, exchangeable and water soluble. So, these are the 5 major forms of molybdenum which are present in the soil environment. First of all, again fixed with the crystal lattice. So, we can see sometime the molybdenum is bound in the crystal lattice, adsorbed into the soil material as an anion. This molybdenum presence in the anionic form, so it can get adsorbed into the soil side where positive charge develop due to pH dependent charge, bound with organic matter we have already discussed, and then it is formed as it is also available as exchangeable as well as water soluble forms. So, let us move ahead and see the predominant ion. What are the predominant ions of molybdenum? The predominant ion is MO4 2-, and this occurs above the pH of 4. So, obviously, when the pH goes beyond 4, then as you know, in the alkaline soil, not alkaline soil, it is basically when the pH is greater than 4, then you can see the predominance of this ion or anion, that is MoO4 2-. Now, pH of the soil solution basically determines the speciation of molybdenum and its behavior in the soil medium. Now, the forms of molybdenum depends on the properties of the soil materials obviously, and secondly on the presence of iron and aluminum oxides. Now, molybdenum remains soluble in the soil with high in organic matter with poor drainage condition, that is from neutral to alkaline range. So, that is why in the alkaline soil they are more prone to leaching. So, another important trace element is nickel. Nickel belong to the group 8 are the stable complexes with many organic ligands, and also under anaerobic conditions sulphide may control the solubility of nickel. So, nickel sulphide is one of the major forms of nickel. Now, sources parent material, just like any other trace element, parent material is one of the major phosphate rock are major sources of nickel. Now, if you consider the nickel in soil environment, very clear so far. Now, nickel sometimes seems to accumulate in the soil layer if organic matter in clay is in high content. So, it is not well defined, but it has got some affinity towards the clay as well as organic matter content. Now, what are the different forms of nickel in the environment? One is the exchangeable sites. You can see the nickels present in the exchangeable sites, specific absorption site fixed with the clay lattice, then adsorbed on the sesquio oxides and fixed in soil organic matter. So, these are the some of the forms in which you can see the nickel present in the soil environment. So, nickel basically occurs in the ionic forms and it is complexed with either organic or inorganic ligands. Now, in soil in general, nickel is, that is nickel with an oxidation number of 2 is basically stable over a wide range of pH and redox conditions. Now, nickel halides and salts of oxoacids are generally soluble in water, while nickel carbonate is almost insoluble. So, nickel, when nickel is present as in halides or oxoacid, it is soluble. However, when it is present as carbonate, it is almost insoluble. So, the solubility of nickel is inversely related to pH. So, as the pH increases, nickel solubility decreases and vice versa. The complexation with organic matter also increases its solubility. When it increases the complexity, complexation with organic matter due to the formation of chelates, then its solubility increases. So, you can see that organic matter, chelation by organic matter increases the availability of most of the availability, or in other words mobility of most of these trace elements in the soil. Another important element is selenium, which is denoted by Se. Now, it is a group 6 element with an atomic weight of 674.96 and it has 6 stable isotopes with the common oxidation states are 0 and 6. Now, what are the major forms of selenium? The stable form in nature is basically selenite. It is the most important and stable form, which is stable under alkaline and mildly acidic condition. Now, if we consider the sources of selenium, what are the major sources of selenium? First of all, volcanic eruption and metallic sulphide associated with igneous activity. So, it is a major source of selenium. Secondary source is different biological pools. From the selenium can occur from different biological pools also. Selenium becomes a pollutant where the parent material are rich in selenium, and industrial sources as well as byproduct of phosphatic fertilizer. So, you can see the industrial production of phosphatic fertilizer can produce a huge number of different elements, specifically trace elements causing its toxicity, and also in case of selenium, specifically volcanic eruption can produce huge amount of selenium, and secondary sources like different biological pools also contribute to the selenium toxicity in the soil. Now, in the soil, the concentration of the selenium generally varies from 0.1 to 2 ppm and then 6 ppm in basically seleniferous soil, that means high selenium content soil basically shows the around 6 ppm. Now, distribution in soil, if you consider the distribution in the soil, selenium accumulates in the soil layer if organic matter in clay is high in amount. It is also found in carbonate debris in sandstorms. So, what are the different forms? In soil, selenium is mainly accumulated in the layers characterized by a high clay content. The forms of selenium largely affect its distribution in the soil profile. The organic form basically originates from from decayed seleniferous vegetations. So, selenium also comes from the plant body. So, decayed plant body also can be an important source of selenium, while inorganic selenium occur as a metal selenites or selenates. So, the predominant mobile inorganic form of selenium is selenite. So, again in soil, selenium is mainly accumulated in the layers characterized by high clay content, and also selenium largely affects the distribution of the soil profile. The organic forms of originates from the decayed seleniferous vegetation. So, vegetation which has high selenium in their leaves can also produce decomposed product which produce the selenium in the soil, while inorganic selenium occurs as metal selenites and selenates, and the predominant mobile inorganic form of selenium is basically selenite. So, what are the different forms? So, in soil, selenium could be biomethylated and can produce volatile organic metabolites. So, it can be biomethylated by different microorganisms and can be produce volatile organic metabolites. This process is a result of soil microbial activity, as just I have told you. So, selenium becomes a pollution problem mainly in the arid and semi-arid areas, as selenium originates from Cretaceous cells which has become an environmental hazard. So, the selenium problem is major, is more prevalent in basically arid and semi-arid regions, and also the selenium toxicity can occur due to uncontrolled agricultural management and also from Cretaceous cells, which are known as major environmental hazards. So, this is about the selenium. The next important trace element is zinc. Zinc belongs to group 2b with an atomic weight of 65.35. It has 6 radioactive isotopes with half life between 55 minutes to 245 days. It has common oxidation state of 2. Total zinc in soil basically depends on the nature of parent materials and then organic matter, texture and pH. What are the sources of zinc in the soils? Basically zinc fertilizer, sewage sludge and atmospheric dust of industrial origin. So, these are the major sources of, so you can see most of the sources are anthropogenic in nature. Different forms of zinc. If you consider different forms of zinc, you can see water soluble forms of zinc are is important, and also ionics are complexed with organic ligands, then exchangeable, extractable, occluded in soil hydrous oxide, precipitated form and constituent of the lattice structure of the clay minerals. So, you can see in all 5 forms the soil in the soil zinc is present. First of all, again water soluble form, then ionics complex with organic ligand just like any other trace elements, exchangeable, extractable, occluded in soil hydrous oxide, it is just like other elements in the soil, and precipitate form and also constituents of the lattice structure of the clay mineral. So, you can see the generalized, it is these 5 forms are more generalized, in which all the most of the trace elements are present in the soils. So, in the soil the concentration basically varies from 0 to 10 to 300 ppm, but a wider range from 1 to 900 ppm is also possible. Now, if you consider the distribution in the soil, zinc accumulates in the soil layer if organic matter is high in amount just like other trace elements. So, basically it produces the complexation with organic matter and zinc complexes with basically humified materials. So, it forms less stable complex with the phenolic hydroxyl and weakly acidic carboxyl groups, while the more stable zinc complex is associated with strongly acidic carboxyl groups, and complexation increases with the humification of the organic matter. So, as the humification of the organic matter increases, complexation also increases. Chelating agents either natural or synthetic are important in defining the zinc mobility in soil, as chelated zinc is generally more soluble in water than elemental zinc. So, basically when we do the chelation, the definition of chelation says it increases its solubility and mobility. So, you can see here zinc mobility is dependent on chelated zinc which are more soluble in water than elemental zinc. Now, what are the influences of pH for the zinc availability in the soil? Now, availability of zinc become very low above pH 7 as its compounds are very soluble only in acidic environment, and redox conditions and also have a pronounced effect on the solubility of zinc, because under flooding condition relatively insoluble zinc sulphide is formed due to the strong reducing condition. So, you know in the when there is a submerged condition, in the flooded condition the redox potential will go down to negative, which will produce the conversion of sulphate to sulphide, and this sulphide will react with zinc to produce a zinc sulphide, and this zinc sulphide is basically insoluble. So, the solubility and mobility of zinc in submerged soil condition varies, and which ultimately depends on the redox potential. Zinc can be temporarily immobilized by bicarbonate hydroxides and organic ligands originating from the decomposition of organic residues, and the zinc fertilizer interaction is basically critical for the trace element solubility. So, zinc also form complexes with nitrogen and phosphorus, and you can see here zinc nitrate, zinc phosphate, etc. you can see. So, it can form the complexes with nitrogen and phosphorus too. So, we have discussed a lot of important potential toxic trace elements, starting from arsenic, then mercury, cadmium, lead, zinc, selenium, then copper, and so on so forth. So, elements also, there are some elements such as antimony, barium, cobalt, fluorine, helium, tin, titanium, and vanadium can also be found in the soil medium as a result of origin, that is parent material, or as industrial residues, or from disposals of as a result of human activity. So, these are some of the other potential toxic trace elements like antimony, barium, cobalt, fluorine, helium, tin, titanium, and vanadium, which can also originates in the environment due to different geogenic activities and also different anthropogenic activities. Now, if this slide basically shows the toxic effects of different heavy metals, and we have only considered here the major heavy metal trace heavy metals like arsenic, cadmium, lead, copper, mercury, and chromium, and their ill effects in the human, as far as the human health is concerned, are given here. For example, in case of calcium, it is important source, it is important for our bones, and it regulate, it is important for our liver, kidneys, lungs, testes, brain, and immunological processes as well as cardiovascular process. And so, obviously, the cadmium toxicity can affect the bones, livers, kidneys, lungs, testes, brain, and immunological processes as well as cardiovascular process. In case of lead, it affects bones, liver, kidneys, brain, lungs, spleen, immunological process, hematological process, cardiovascular process, and reproductive process. Copper toxicity influences liver, brain, kidneys, cornea, gastrointestinal, and then lungs, immunological process, and hematological process. Mercury influences mainly brain, then lungs, kidneys, liver, immunological, cardiovascular, endocrine, and reproductive process. In case of chromium, it affects skin, lungs, kidneys, liver, brain, pancreas, testes, gastrointestinal system as well as the reproductive system. And arsenic, it impacts the skin, lungs, brain, kidney, liver, metabolic system, cardiovascular system, immunological system, and also endocrine system. So, you can see these are the major heavy metals which are producing toxic effect for human body, and these are some of the major areas in which it can produce the toxic effect or toxicity effects. So, we have covered the important toxic inorganic pollutants. Now, we are going to start the toxic organic residues. So, the molecular properties of the toxic organic chemicals are basically electronic structure, their water solubility and the ability to volatilize. These are the three major important molecular properties of the toxic organic chemicals. One is electronic structure, then water solubility, and third is the ability to volatilize. Now, toxic ionic organic chemical interaction with the soils are basically pH dependent. So, for non-ionic compounds, aqueous solubility, that is hydrophilic property, is the most important molecular parameter correlated with the with sorption, and highly soluble anionic chemicals exhibit low affinity for the soil surface, while opposite holds true for the chemicals of low solubility. And there are also other molecular properties relevant to chemical behavior of soil, such as shape, size, configuration, polarity, polarizability, acidity and volatility. So, all these are other molecular properties relevant to chemical behavior of soils, and these are the important properties like shape, size, configuration, polarity, polarizability, acidity and volatility. So, so this is basically an overview of toxic inorganic substances. So, let us move ahead and see the classification of the toxic organic residues. So, if you see the classification of toxic organic residues, they are basically here you can see the toxic organic residues can be subdivided into small organic molecules as well as organic macromolecules. So, what are the differences between these small organic molecules and organic macromolecules? We will see. So, let us start with the small organic molecule. So, organic chemicals which are characterized by small molecule reach the soil surface mainly as a result of crop protection practices or during the land disposal of industrial wastes. So, mainly this type of small organic molecules are comprised of the pesticides which we apply for our crop protection. So, these pesticides contains huge amount of these trace elements or heavy metals which can further which can further produce toxicity effect to the environment. Now, pollution due to pesticide is considered as a non-point source pollution obviously. So, because pesticides are applied in different agricultural fields, and as a result of that, when there is a rainfall and subsequent runoff due to the rainfall, then this pesticide will move along with the soil particles and creates a non-point source pollution to the nearby water bodies. Now, pollution due to industrial residues is considered as a well defined point source, because whatever industrial byproducts or effluents are we are getting is basically discharging, they are discharging into the water bodies through a well defined point source. So, that is why it is a point source pollution. Now, after reaching the soil, various degradation and transfer process basically occurs. Now, the chemical properties of the compounds such as molecular structure, ionic charge and ionizability, polarizability, volatility and water solubility basically determines the process. These basically determine which process will be will predominate. So, again small organic molecules basically consist of the pesticides, different types of pesticides, and these pesticides pollution is considered as a non-point source pollution. However, the various effluents and byproducts from the industry are known as the point source pollution, and when they reach into the soil, they produce different types of degradation and transfer process, and the chemical properties of the compounds such as molecular structure, ionic charge and ionizability, polarizability, volatility and waste and the water solubility will determine which process among these, like non-point source pollution or various degradation or transfer process will be predominant. Okay. So, let us see those in details. So, different small organic molecules. If you consider different small organic molecules, we get there are three major classes. One is pesticides, another is hydrocarbons, and third is phthalates. So, we will discuss these pesticides, hydrocarbons and phthalates from the point of view of their toxicity in the soil environment. As you can see here, this is a pesticide spraying into the field, creating a major source of soil pollution sometime, because these pesticides are very much persistent in the soil environment. Okay. Now, pesticides are again can be classified into four major types. One is cationic organic molecule, second is basic organic molecule, third one is acidic organic molecules, and fourth one is non-ionic organic molecules. Okay. Again, cationic organic molecules, basic organic molecules, acidic organic molecules and non-ionic organic molecules. So, you can see in this picture, it is called it is showing the fate of pesticides in the soil. So, when we apply the pesticide into the soil, some amount of pesticide get absorbed into the soil due to the due to the presence of different clay minerals as well as organic matter, and from there it becomes bioavailable to different organisms. And also from the direct pesticide application also some amount may come into the may become bioavailable. Now, from this bioavailable pool, plant uptake accounts for one of the major so from this bioavailable pool plant uptake occurs, and also from this bioavailable pool you can see biodegradation by different microbes, and also this pesticide will go go to leaching from these bioavailable pools, and ultimately it reaches the groundwater. So, this is one of the major source of pesticide pollution, and also from the bioavailable source some amount get volatilized into the atmosphere, and a part of this volatilized pesticide again come back into the soil solution, return into the soil solution through rains. So, you can also see due to the application of pesticide into the leaves. So, it can also come back into the through the falling leaves. So, plant uptake can incorporate these pesticides into the leaves and bodies, and through the falling leaves they can also come back directly into the soil. So, this is basically showing, this slide is comprehensively showing the fate of pesticide in the soil. Again, we are applying the pesticide, is certain amount of pesticide getting absorbed, and other portion is getting bioavailable. Some portion of adsorbed soil is converted to the bioavailable form, from where plant basically uptakes, also biodegradation occurs and leaching occurs and volatilization occurs, and the volatilized pesticide residue can further come back, return to the earth surface in the form of a rain, and this plant uptake can produce the this pesticide accumulation in the plant body, which can further return to the soil through the falling leaves. So, this is basically fate of pesticides in the soil. So, if you consider, so we have seen there are four groups of pesticide. One is cationic organic molecules, basic organic molecule, acidic organic molecules and non-ionic organic molecules. So, if you consider on the cationic organic molecules, bipyridinium herbicides such as diquat and paraquat are the major compounds from this group, cationic organic molecules. So, you can see this is a cationic organic molecule, here this is diquat and this is paraquat. So, those herbicides that belong to bipyridinium quaternary ammonium class are characterized by a positive charge, you can see here, and and are also heterocyclic compounds. So, diquat and paraquat are mainly contact herbicides. So, basically they kill the herb or kill the weed just by direct contact. By direct contact it can kill the weed. So, that is why it is called contact herbicides, but may also be used as a aquatic biocides. So, these are the two major examples of cationic organic molecules. So, these cationic organic molecules are available commercially as dibromide or dichloride salts, and they are characterized by high solubility in aqueous solutions. In aqueous solution, they dissociate readily to form divalent cations, and diquat and paraquat are non-volatile and do not escape as vapor from aquatic or soil systems, and they are readily photodecomposed on exposure or to sun or UV light, but are not photodecomposed when adsorbed onto the particulate matter. So, they are readily photodecomposed due to the presence of sunlight or UV light. However, when they are adsorbed into the particulate matter, they are not photodecomposed. The second one is basic organic molecules. So, several members of the S-triazine family were selected as an example of basic organic compounds. Now, the triazines are heterocyclic nitrogen derivatives, and the ring structure being composed of nitrogen and carbon atoms, as you can see here. This is a symmetrical triazine, this is an asymmetrical triazine. So, most triazines are basically symmetrical, and the substituent and you can see the substituent at R1 position determines the ending of the common name. So, these are the examples of basic organic molecules. So, guys, let us wrap up our lecture here, and we will start from here, and then we will discuss in the next class the basic organic molecules and also acidic organic molecules and other organic macromolecules. Thank you very much. Let us meet in our next lecture to complete this week or this module 8. Thank you very much.